Here I'll be explaining analog multipliers, Gilbert multiplier cell in particular. A multiplier produces an output V0 which is proportional to the product of two inputs, that is Vx and Vy. Here we can see in this equation V0 is equal to K Vx into Vy, where K is the scaling factor. There are different methods for performing analog multiplication. They are logarithmic summing technique, pulse height or width modulation technique, variable transconductance technique, and multiplication using Gilbert cell. Actually, multiplication at the output means we expect only Vx and Vy, but product of Vx and Vy. But here we can see that there are offset voltages and also error signals at the output. Here, first we are going to learn a simple multiplier using emitter coupled transistor pair. For that, we have to know first what is an emitter coupled pair is. We can see in an emitter coupled pair the relationship between IC1 and IC2 with the differential input V1 is given as this, that is IC1 is equal to the current over here divided by 1 plus e raised to minus V1 by Vt, and similarly IC2 also similarly, that is now in denominator we have got 1 plus e raised to V1 by Vt, and here we have minus V1 by Vt. This is the relationship between the current and voltage in an emitter coupled pair. You have to keep this in mind, and Vt is the thermal voltage. So the difference between the two output currents, we can take it as this, and we can reduce this to write it as tan h into V1 by 2 Vt, because of this relationship between tan x and exponential, that is 1 by 1 plus e raised to minus 5 minus 1 by e raised to plus 5 is equal to tan h 5 by 2. So using this relation, we can minimize this as IEE into tan h V1 by 2 Vt. So we can approximate this tan h V1 by 2 Vt as V1 by 2 Vt. Therefore, we can write it like this. Therefore, we will get delta IC is equal to IEE into V1 by 2 Vt. IEE is the bias current for the emitter coupled pair. So we can make this IE proportional to a voltage. Here we are going to study a multiplier cell. So we need two voltages. Here we have seen an emitter coupled pair, just an emitter coupled pair. So we need two voltages for a multiplier input, that is V1 and V2. So here in this emitter coupled pair, we have seen IC, that is the difference in the current at the output. IC is equal to the product of a current IEE and V1 by 2 Vt. So we are now going to represent this IEE in terms of a voltage. That is shown in this circuit, that is the IEE is made with the help of a voltage V2. Thus IE is replaced by this portion of the circuit, and this is a current mirror circuit. So here IEE is equal to K0 into V2 minus VBE on. That is, we will get a current over here, that is V2 minus VBE on. The voltage here minus V2 by R. V2 minus VBE by R will be the current in this branch. The current in this branch will be similar to that of this branch. Therefore, we can write IEE is equal to V2 minus VBE by R. So we have got the IEE in terms of V2. Therefore, we can write delta IC is equal to V1 by 2 Vt into IEE, and we have replaced this IEE in terms of V2, that is K0 into V2 minus VBE on. So this is a simple multiplier cell. So we have not got into Gilbert multiplier cell. We have just seen a simple multiplier cell. And the limitations of this simple multiplier cell is that V2 is offset by VBE on, and also the voltage V2 must always be positive, which results in only two quadrant multiplier operation. That is V1 and V2. Out of V1 and V2, V2 must always be positive. We know there are four quadrants in which V1 and V2 can be positive, one can be negative, the other can be negative, and both be negative. So in this particular multiplier, only two cases are possible. That is V1 is positive and negative, and V2 can only be positive. Therefore, it can occupy just two quadrants. That is, V2 should always be positive in order for this current mirror to work properly. Therefore, we cannot give a negative voltage for V2. So it's a limitation for this simple multiplier cell. And also the third limitation is that tan Hx is approximated as x, where x is equal to V1 by 2 Vt. It is approximated. And these are three limitations of a simple multiplier cell. And next we are coming on to the Gilbert multiplier cell. The first two limitations of this simple multiplier are overcome in a Gilbert multiplier cell. See, this is a circuit diagram for a Gilbert multiplier cell. If you understand a simple multiplier cell perfectly, then it will be easy for you to understand the Gilbert multiplier cell. So you have seen, we can see here that this is an emitter coupled pair, this is another emitter coupled pair, and this is another emitter coupled pair. These two emitter coupled pairs are cross coupled, and this cross coupled pair is connected in series with another emitter coupled pair. So it is a modification of an emitter coupled cell, and it's written here. It consists of two cross coupled emitter coupled pairs in series with an emitter coupled pair. So now we can look into the current relations in this circuit. Here the collector currents of Q3 and Q4 are given by these equations. See, these equations is it's the general relationship of the emitter coupled pair, which we saw in the first few slides. See, this is a general equation. The current over here divided by 1 plus e raised to minus V1 by Vt. The same relationship is used here. So you can understand if you compare the circuit and the equation. So we see IC3 is equal to the current over here divided by 1 plus e raised to minus V1 by Vt. See, the current over here is IC1 divided by 1 plus e raised to minus V1 by Vt. And IC4, the current over here is equal to IC1 divided by 1 plus e raised to plus V1 by Vt. See, likewise IC5 and IC6. That is the collector currents of Q5 and Q6. So we have got the collector currents of all the transistors, Q3, Q4, Q5 and Q6. Next we are moving on to the collector current of Q1 and Q2. Q1 and Q2. Here we have got we can write it in terms of IC1 and IC2. We can write it in terms of IEE. IEE divided by 1 plus e raised to minus V2 by Vt, and similarly we can write IC2. So we are here we have to substitute equation for IC1 in equations of IC3 and IC4. That is, in equations of IC3 and IC4 we have to substitute IC1. So we'll get all the equations in terms of IEE. So the differential output current, that is delta I, is equal to IL1 minus IL2. See the circuit, the final currents IL1 and IL2, the difference in output currents IL1 and IL2, we will get it as IC3 plus IC5 minus IC4 plus IC6. IL1 is the sum of IC3 and IC5, and IL2 is the sum of IC4 and IC6. And we can rewrite this equation like this, and on simplifying this we will get delta I is equal to IEE into tan H V1 by 2 VT into tan H into V2 by 2 VT. And this is a 4-quadrant multiplier. That is, we can have both plus and minus values for V1 and V2. And also, it can be used as a modulator. That is, there we have got two voltages. Therefore, we can use a modulating signal and a carrier signal, and we can use it as a modulator also. And this is all about Gilbert multiplier cell. Thank you.